Okay, so we've been talking about Lean and logic, and I've showed how to prove some very simple tautologies in Lean, which are a bit like doing the scales on the piano. But now we maybe want to play a little song, a very simple song, I mean nothing complicated, uh, and like Twinkle Twinkle Little Star, you know. And the Twinkle Twinkle Little Star I want to play is my favorite song, and it's proving something about the reverse function, right? So here I define reverse, and how do we define reverse?
Well, last time we did anything with reversing, it was using recursion.
Recursion, right? So the idea is to reverse the empty list is the empty list, and to reverse a list, a cons list, which is a list which has an element in front, we reverse the tail and then put the element in the end. And now we need an auxiliary function, which I call snock, because snock is cons backwards. So cons puts a list in the beginning, and snock is now an auxiliary function, which puts an element in the end. And it's also defined by recursion. So yeah, so my reverse works. Reverse of 1 to 3 is 3 to 1, and maybe to explain snock, if I have a list 3, 2, and put a 1 in end, I get 3 to 1. So that's the idea. Now the observation, so the song I want to play is, if I reverse twice, I get the same list back. And we have already looked at this in ACTA, and today we do it in Lean. So I want to prove this theorem here, and let me make this look a bit nicer. So the A is upside down is a symbol. It means for all, right? Just read the A upside down for all. For all A's, which are list of A, it is the case that if you reverse them twice, it's the same as you begin. And now we want to prove this statement. We have to prove something for all lists. So we saw the same tactic as we used when we proved A implies B. You say assume given a list A's. So then we have an assumption given A's as a list, we have to prove the statement. So how do we prove a statement over all lists? So to prove a statement over all lists is very similar to recursion. To prove a statement for all lists, you prove it for the empty list, and you prove it for the cons list, and when you prove it for the cons list, you can assume it already holds for the tail. So that's the principle of induction, which we usually know for numbers, but it also works for lists. We say so I say I want to do induction over the list A's, and then I give it some names which it should use. And when I say this, and I get, in this situation, I say I have to prove it for nil, so it's one of the goals I have to prove. And I have to prove it for the cons, you see here. But when we prove it for the cons, we have an assumption that it already holds for the list B's, which is the tail. Now to prove it for the empty list is very easy, because ref of nil is nil, and if you reverse nil twice, that is thus the empty list. So that just proves, we just say reflexivity, we prove it. It's done. We only have to prove the cons case. And to prove the cons case, okay, let me first of all run this program a bit. This is called dsimp in simplify. And what happens is that it uses the definition of, so if you go back before, we had ref, but the definition of reverse of a cons is to reverse the tail and snock the beginning at the end. And if we apply this, if we run this program one step, then we get into this situation. Now here on the right hand side we have an A in front, and here is the A in the end, but we reverse it. So now the art of proving something is to come up with the right auxiliary theorem, which is called a lemma. And so the right auxiliary theorem in this case, so here is my auxiliary theorem, or my lemma. Namely, what I wanted to do is, what I needed is if I reverse a snock, it's the same as consing the reverse. Yeah? So putting an element at the end of a list and then reversing it is the same as putting the element in the front and reversing the tail. So I'm not proving this in the moment. I just assume, let's say, if we had this, what can we do? Yeah, now we are in the situation. Now, if I now use my lemma, if I say rewrite ref snook, then okay, what happens? Before we had this snook at the A in the end and then reversed. But if we do this one step, we now got the A in front on both sides. So we really looks good. And all we need is that ref of b's is the same as b's, but this is exactly our assumption, our induction hypothesis. So all we have to do is to rewrite this IH, and we are done. Now we are not really done. Why are we not done? Because we haven't actually proven this theorem. So now, or this lemma. Now I will cheat a bit and put my so here's a all of a sudden by magic I have very quickly proved this lemma. I've done another induction and it works. And now putting both together, we have proven the whole theorem. Okay, so that's our first song in Lean. But let me also close with a little challenge. So my challenge is this program reverse, which I've written here, is actually quite inefficient. It has quadratic complexity because it goes through this list, and then for every element it uses snock, and snock again goes through the whole list. So it has quadratic complexity, which is not good because reverse should be linear. So now we can write another version of reverse, which is called fast reverse, which basically it uses the second argument, which is called an accumulator. So it accumulates the result in the second parameter. And when the first list is empty, it just returns the accumulator. And if the list is non-empty, it puts the element in front of the accumulator. And if you think about it, that means that the whole list is accumulated in reverse. And now using this function with the accumulator, we start with the empty list as the accumulator and run it through the list. And if you see here, this also reverses. But the nice property of this function is that it's only linear because it goes through the list only once instead of twice. And now this is a common situation. We have written a program, maybe it's a very simple program, we understand, we have proven something about it. Like if you reverse twice, you get the same result. And now we have this fast function. And we want to use it because it's better, but it does the same job. So, but we have to prove it does the same job. So here, what we want to prove is that fast ref and ref give always the same answer. So that's a challenge. A little hint. So yeah, we have to use list induction. So the first step here is to do induction over the list. Prove it for the empty list. It's actually quite easy. And then prove it for the cons. But then you need a lemma, and the lemma will involve this ref aux, because you have to prove something about ref aux to be able to prove the theorem. And the challenge is mainly to come up with the right lemma about ref aux, which enables you to prove this theorem and then actually to prove it.